I very vaguely saw some papers on billiard systems where they looked at, I don't know if they made them like quantum mechanical or just looked at like probability distribution of trajectories on these systems, but they showed that
Yeah.
like the orbits, at least the longer orbits, had a lot
Yep.
of correspondence with certain like eigenfunctions of the probability.
Yeah, absolutely.
distribution.
So this is something that we'll be talking about much later. But it turns okay. This is a tirade. If this doesn't make any sense to you, feel free to tune out. But I'm just sort of going to give the broad idea. So the basic idea is actually that for long-term view of chaotic systems, the deterministic viewpoint is totally broken. The existence of positive Lyapunov exponents, or even less than that, even just like separation of trajectories on a linear timescale, basically makes deterministic understanding of the long-time behavior totally useless. So how do we get around that? The way we get around that is by understanding the probabilistic viewpoint of these systems. So that's where we switch over from a topological transitivity statement to an ergodic statement or a mixing statement to better understand these systems, because like Predrag was telling us in the first lecture, the idea that we can know our initial condition with absolute certainty is like totally bankrupt. It's never been done before, and it never will be done. We switch over to this probabilistic statement. You pick up a whole new set of tools there. And one of the tools related to this is analysis of the associated Koopman or transfer function. Don't worry if you don't know what any of these words are. We'll be going over these sorts of things, I believe, in like week 9 or week 10. What you can ask is, okay, what probability distribution do my billiards settle into? And one of the ways of understanding that is by looking at eigenfunctions of the transfer operator. So the transfer operator, if you have a discrete dynamical system, the continuous case is totally analogous. I'm just not going to do it. So we get a Koopman operator, which acts on observables, which sends some let's say our dynamical system is given by some map T from a state to itself. Okay. The associated Koopman operator sends some observable. So phi is in, let's say, the continuous functions on our space, sends phi to precomposition with our dynamical system. So this is like asking, if you know the function value now, where does that map to in the future? Okay. The adjoint of this, which acts on probability distributions, is known as the transfer operator, the push forward, the Perron-Frobenius operator, whatever you want to call it. Okay. And one of the things is that if your system is measure preserving, which, sorry, I didn't talk about that, but billiards is Lebesgue measure preserving, because if you imagine sort of a blob in billiards, so imagine I have a blob of initial conditions, they're all just going to move forward according to their conditions, and for each initial what's called velocity vector, and then you basically do the argument across every velocity vector. So there's lots of technical details there that I'm not going to go into, but that's the idea. So
I'm sorry,
so
wait,
you
can I
know
just
that
ask
this.
real quick? So did you say that
Yeah.
the Perron-Frobenius operator is the adjoint of the Koopman operator, or did I mishear that? Interesting.
Yes, no, that's right. Yeah. So the Perron-Frobenius operator acts on measures. The Koopman operator acts on functions or observables. Perron-Frobenius operator acts on measures. And there are some weird differences. So there's a whole way of dealing with dynamical systems called the transfer operator method, where instead of studying the dynamical system directly, you study the spectral properties of its transfer operator or its Koopman operator. You can study either because the adjoint preserves the spectrum, so you can study either. And the idea is that, like, let's say that this is all possible spectrums. You can show pretty quickly, just based on measure preservation, that it's bounded in norm by 1. And you know that there's always an observable which corresponds to the eigenvalue of 1, given by the constant observable over your whole space. And so the question is this the only eigenvector corresponding to an eigenvalue of 1? Okay. And we're not going to go into technical definitions here, but what does mixing mean from a spectral picture? Strong mixing, which is sort of what most people think of as mixing, it's the mixing that happens when you put cream in your coffee and swirl it around, where everything sort of homogenizes. What does that correspond to at the transfer operator level? That corresponds to what's known as a spectral gap. So you have a unique eigenvalue, besides the trivial one, here at 1, and then the entire rest of the spectrum is separated by some finite gap from the edge of the circle. And so everything just sort of dies down, and you're left with just this single distribution, which is given by, which is the invariant measure for your system. So this is a sort of a different way of handling things. And would I assume the paper you saw was maybe talking about was switching from understanding the billiard from the level of geometry to looking at the transfer operator, and then trying to look for invariant measures via the spectral approach?
Yes, I think so. And are we going to be looking at, so are we going to be looking at this system like in that perspective, I guess, later in this course?
So my understanding is that we will talk about the spectral theory, but I don't know how much we're going to get into the transfer operator method as a whole. I can give resources for that. There's some great course notes by Sarig on this method in particular, and how you can, there are some techniques for not necessarily proving compactness of transfer operator, but by proving quasi-compactness, which is very helpful because it essentially turns the spectral problem into a linear algebra problem, which is much more tractable. We're going to introduce the notions of how probability works into the chaotic dynamics, but we're going to spend a lot of time talking about the topological consequences as well. So we won't spend so much time talking about the probabilistic viewpoint, because we'll be spending time talking about things like zeta functions and cycle expansions